steps. Remember now, when you're differentiating, you're going up the steps. When you're integrating, you're going down the steps. Now, we're going to talk about this in a little different method. I know that it goes position, velocity, acceleration. We can also talk about this, and oftentimes in calculus problems, we talk about this. We talk about this as an amount. That may be in miles. That might be in people. That might be in gallons. That might be in bananas. So it can be in anything, amount of something. When you go up a step, what we get is we get a rate of the amount. So you got the rate of the amount, it's per something. So it's per minute, per hour. It could be per PSI, like the example that's right next to it. It could be per day. Oftentimes it's a time measurement, honestly, but it could be something else, but you got to kind of think of it. Think of it as a per something. The last step then is the rate of the rate of the amount. Okay, so the last step is the rate of the amount. So you're moving up and down these steps. You're given something and then you're asked something else. So this is going to be per that time or that per thing squared. So per minute squared, per hour squared, per PSI squared, per day squared. So it's whatever that is, one more power of that thing. So when you think about like this one, atmospheric pressure of the air changes with height above sea level. The height above sea level at a given pressure can be measured by a differentiable function. F of P is in miles, where P is measured in PSI. What are the units of F double prime? Well, if F of P is in miles, then that would be right down here. Then F prime of P would be in miles per PSI, because that's the independent variable. And then F double prime of P would be miles per PSI squared. So that's why this is going to be the answer. Okay? So you got to kind of figure out what are we given and where are we going? Let's see if I can find one that moves down the steps. So take something like this. Now this is an interesting one. So you got to kind of think about what this is. Let's just think about what the integral is. Just that part. Notice that it says F of T is measured in centimeters and T is measured in minutes after the storm. Okay, so centimeters, F of T is measured in centimeters and T is measured in minutes after the storm. So notice that we have here that we're dividing by some sort of a minute, but then this is really walking down a step, but this is canceling that down a step. So I think this is going to be measured in centimeters. So if you think about it, let me go back. Let me show the question again. This right here is really the average value of f, right? I mean, that's the average value of f. That's how we do the average value, 1 over b minus a, the integral from a to b of this function f. So if that's true, then this is the average value of F, and F is measured in centimeters. So our answer is centimeters on that one. So you got to kind of figure out where are we and what are we trying to get to. AP will oftentimes do problems like that. So then you're going to also get problems like this, where oftentimes on AP problems, they're going to give you some sort of a rate in, and they're also going to give you a rate out. Maybe they're measured in gallons per minute, for example. And then they'll ask you about an amount. How much came out of this thing? Well, sometimes rate in, gallons per minute, rate out, gallons per minute. If you wanted the amount from, let's say, some time interval A to some other time interval B, well, think about what we have. We have rates and we want amounts, so we're going down the steps. But in this case, we have to integrate from A to B, the rate in minus the rate out. Because we got to figure out, well, how much is going in, how much is going out? And the integral of the rate in minus the integral of the rate out would give us the amounts left. So water is being pumped into a tank at a constant rate. So here is the in, pumped in, constant rate at that many liters per minute. Water is being removed from a tank at a constant rate given by that. What is the total amount of water in the tank at time t equals 6? Well, notice it says the tank has 150 at 0. Okay? It has 150 at 0. So if we think about this rate in or rate out, then the amount at t equals 6 is how much did we start out with? Well, we knew there was 150 in there before we even did anything. And what we're going to do is we're going to add a certain amount. We're going to add a certain amount from 0 to 6. But that's going to be based on how fast it's pumped in. In that case, it's pumped in at 13, minus how fast it's being pumped out, which is Q of t, dt. And you're going to use your calculator on that. I mean, that's a calculator problem. Remember, go back to the previous video. We talked about how to do that on the calculator. You can do math or menu. Is it menu? Calculus. Integral. And then just once you do that, it generates this integral from whatever it is. It generates this kind of a thing here that you just have to fill in. But the key is, can you come up with that? So when I show the solution, notice that that's what they are doing here, right there. 150 is what we started with, 0 to 6 of this many liters pumping in and pumping out. So let's go back. Absolute extrema, same kind of thing. Only remember, when you're doing absolute extrema, you're checking the critical numbers and the endpoints. Well, the critical numbers, when you're thinking about like critical numbers in this case, critical numbers for absolute extrema with this kind of thing is when the rate in is equal to the rate out, or the rate in minus the rate out is equal to 0. because we need to create some kind of an equilibrium. That's where critical numbers are going to happen. So absolute extrema critical numbers are going to occur when this happens. So it's really going to be important to kind of note that and come up with this table. So notice that this one is saying the tank has 20 liters at time t equals 0. And notice down here it says, what is the minimum amount in here? We have a rate pumped in. We have a rate pumped out. So we're going to use our calculator to kind of come up with where those two things intersect. We might do it I'll do it off of a Desmos calculator, but the idea is the following, is you kind of go, okay, I know that I'm going to have this interval, and we're going to put this amount here. And notice this amount is going to be that 20 plus the integral from 0 to t, whatever that is, of the amount being pumped, or the rate at which it's being pumped in, minus the rate at which it's being pumped out. Okay, so that's what we have. We know at 0, there was 20 liters in the tank. We know at 5, we could figure out, well, we could do 20 plus the integral from 0 to 5 of z of t minus h of t. We could do that on our calculator. We could put those equations in on our calculator. The key on this is kind of going, okay, well, what are we going to do in the middle? So what we can do is, I know you guys have a graphing calculator that you really need to get used to using, because you're going to have to use it on the AP exam for a problem just like this. So if I take this, I don't know if I'll be able to copy it, but I'm going to give it a shot. Nope, that won't let me do it. So I'm going to have to write it down, and I'm going to just pull this window down so I can see both of them at the same time. So if I type this in, I got negative 10 times 1, or sorry, times 0.69 to the x, likes using x, so I'm going to use x, plus 17. So that's the rate in. And then I'm going to do the rate out, which is negative 5. And then I'm going to do 0.76 to the x plus 14. And you could do that as well. Now notice, these two things intersect right there. So the black one is the rate at which it's being pumped in. The red one is its rate at which it's removed. Notice that as long as the red one is above the black one, more water is going out of the tank than in the tank. So we need to use this value right here, that value right there, 1.067. That's the value we need to use. That's this value, 1 over here, 1.067. And you really probably need more than 3 decimal places, but that's our critical number. That's the critical number that's in there. Now, on an AP exam, you want to say z of t equals h of t at t equals 1.067. For an FRQ, that's an important piece. This is 1 point on an FRQ. The table is another point, and the answer is the third point. So now this would be 20 plus the integral from 0 to 1.067 z of t minus h of t. And then you'd go through and solve it. And I'll show you what they, see if they do the same kind of thing on here. Yeah, so they use it on there, and then they show you. So the absolute minimum is right there. You should know that the absolute minimum is right there because every time before the rate in the rate out is bigger than the rate in, and after the rate in is beating the rate out. So this turns out to be 19.015, and that right there is our absolute minimum. So same kind of things that we're doing before, but now we're just applying it to a rate in and a rate out situation. So no really new context. Take something like this. You're going to have to answer this one, and I think I'll probably throw this one up a little earlier in this. The rate at which people are entering a sports arena in people per hour can be modeled by this. So here, this function is people per hour. So let's go back up. People per hour would be maybe right here, people per hour. Determine the value of f prime of 5. So f prime of 5. Now we're going up a step, right? And we're going up a step. So the unit of measure at the very least is going to be people per hour squared. Now I don't know if Desmos will let me do derivative. I don't know if it'll let me do derivative. So I don't think I can do that on there. Maybe I could do it on this. So let me try it on this one. Let me try it on my calculator here. This is an 84 calculator. It's the same kind of thing. But what I can do is I can go to math, and I can go to number 8 is my derivative on this. So if on yours you just do math calculus and you get and you have number 1 there. So I'm going to do 48, and then I'm going to do cosine, and I'm going to do 0.02, and then I'm going to do x squared. So where's my squared button? There's my squared button. And then I'm going to make sure I evaluate it at 5 and hit enter. And I do need to make sure my mode is in radians. So it is, so that's good. So I think that that's going to be my value. I'm not sure if they're going to give it to me in there it is. There's my same value, and it's people per hour squared. So that's my value right there. So that's another one on how you have to do that. So again, it goes back to the steps. So we haven't really learned anything new. We've just kind of applied things a little bit differently. Hopefully that makes sense. Hopefully you understand what's going on. If you have any questions, please feel free to ask me.